Welcome to the Joy of Architecture. Have you ever been stuck waiting for a web page to load, maybe a big report to finish generating, and it just hangs? Often the silent force behind that experience, for better or worse, is something called a database index. Today we're going to pull back the curtain on database indexes, those organized data structures working behind the scenes, really dramatically speeding up how we retrieve information.
That's exactly right. Indexes are, well, fundamental. They minimize disk operations, make databases incredibly fast, reliable. But here's the rub. They come with these fascinating trade-offs. Storage, maintenance, overall performance. It's never really one size fits all. Choosing the right index. For your specific data, your workload, that's a blend of art and, well, engineering.
Right. So our mission in this deep dive is to cut through that complexity, give you a rigorous but still easy to follow understanding of how these different index types actually work, where they truly shine, where they stumble, and maybe most importantly, when and why you should choose one over another. This is for anyone looking for that real aha moment in database architecture. So, okay, let's kick things off with the most common index type, the B tree and its close cousin, the B plus tree. These are foundational. What makes them so versatile?
Yeah, the B tree and B plus tree are, they're ubiquitous. And for good reason. Think of them as these incredibly organized, self-balancing tree structures. In modern systems like, say, PostgreSQL or MongoDB, you're mostly seeing B plus trees. And the crucial design choice here is that all the actual data or pointers to it live exclusively in the lowest level, what we call the leaf nodes.
Ah, okay, so the internal nodes are just navigational guides, like a directory.
Exactly, just telling you where to go next, not holding the full info themselves. And this design, it allows for a very high branching factor, meaning each internal node can point to many, many child nodes. The practical impact, it creates a very shallow tree. Fewer hops, fewer disk I/O operations to find your data.
Right. Fewer reads from disk, which is always the slow part.
Always the bottleneck. That's paramount for disk-based systems. What's also key is that those leaf nodes, they're linked sequentially.
Sequentially, so like next to each other. And that must be huge for certain types of queries, right? Like finding everything in a range.
It's a game changer, absolutely. Those linked leaf nodes make range queries incredibly efficient, whether you're filtering data between two dates or asking for values greater than something. It also helps immensely with order by clauses for sorting. Under the hood, searching is like a quick binary search down the tree, inserts, deletes, they adjust the tree, sometimes splitting nodes, sometimes merging them to keep it balanced.
That sounds like ongoing work. Rebalancing, does that actually impact performance much in the real world? Or is it mostly managed well now?
That's a really critical point. Modern B trees are incredibly robust. They've mitigated a lot of write overheads. Things like MVCC, multi-version concurrency control, lets reads and writes happen without blocking each other. Or PostgreSQL's hotkey updates, where small changes don't always need a full index update. But the core insight for architects is this. B-trees are phenomenal generalists for balanced read-write loads.
Okay.
But if your application is truly write-only, like extreme scale, that rebalancing overhead, it'll still point you towards specialized structures, like LSM trees, which we'll get to.
Got it. So they're the default general-purpose index, but not a silver bullet. Where do they really excel and where do they kind of fall short?
B-trees. B plus trees, they're your go-to for point queries, exact lookups, range queries, sorting, also excellent for prefix matching, like ABC %, and enforcing uniqueness constraints. That's why primary keys almost always use them. You'll find them as the default in, well, basically all relational databases, PostgreSQL, MySQL, Oracle, and even in document DBs like MongoDB's Wired Tiger. But yeah, they aren't optimized for full text search or for multi-value types like arrays or JSONB. Those need something else. And for very low cardinality fields like a true-false column, the overhead might outweigh the benefit.
Okay, that makes sense. So if B trees are the great generalist, where does a hash index fit in? I hear it can be even faster for some very specific tasks.
A hash index is built for one thing. Blindingly fast, exact match lookups. That's its specialty. It uses a hash function, maps a key directly to a storage bucket or a memory location. It's basically a hash table. To search, apply the hash function to your key, bang, it points you right to the bucket. If multiple keys hash to the same bucket, that's a collision. The index has ways to handle that, often linking them.
Right, collision handling.
Yeah, that's key to performance, but also part of the maintenance overhead.
So it's almost like looking something up directly, like page 52 in a book, no index needed, super fast. What's the trade-off then?
You've hit it. It's a specialist. It offers amortized O1 for lookups, meaning on average, incredibly fast, almost instant. But it's Achilles' heel. It preserves no inherent order, none at all. So completely unsuitable for range queries or sorting or prefix matching. Can't do it.
Okay, zero order, big limitation.
Huge. And also, if the table grows a lot and needs resizing, rehashing all the existing entries, that can be really expensive, especially if it's on disk, which is why they truly shine in memory databases, where that random access latency is basically negligible.
Right. So the key takeaway, don't reach for hash if you need any kind of ordering or range filtering. Precision tool.
Perfectly put. It's for that precise, lightning-fast equality check, often used for uniqueness on IDs. You'll find them in PostgreSQL for equality, SQL Server's memory-optimized tables, MongoDB for hash-based sharding sometimes, great in OLTP for specific fast point lookups, not for analytical queries, though.
Okay. Shifting gears a bit towards the analytical side, bitmap indexes. They sound different working with bits. What problems do they solve?
Bitmap indexes are, a radical departure. They represent data using bit vectors. For each distinct value in a column, you get a separate bit vector. Each bit in that vector corresponds to a row in the table. 1 if the row has the value, 0 if not. So for like a gender column, you'd have 1 bitmap for male, 1 for female.
Huh. So very compact for columns with few distinct values.
Exactly. Incredibly space efficient for low cardinality data. And the real power is querying. Complex Boolean operations, AND or not, can be done directly on these bit vectors, and it's extremely fast.
Wow, leveraging bitwise speed.
They
Updates flipping a bit sounds simple, is it?
It sounds simple, but that's where they really struggle. Updates can be very inefficient, often involves complex decode, flip and code steps if they're compressed, sometimes even full index rebuilds. And because there are fewer distinct values, those few bit vectors, they become hotspots for locks during updates. Serious contention in concurrent environments.
Ah, okay. So definitely not for dynamic, constantly changing data. Where do they shine then?
They're specialists. Best for low cardinality columns, status codes, Boolean flags, that sort of thing. And in read-intensive OLE data warehousing workloads, they excel at complex queries with lots of ANDs and ORRs. And for aggregations, you find them in Oracle, StarRox. PostgreSQL has Brin, which is related, serves a similar goal for large clustered data, so very fast reads for specific queries, space efficient for low cardinality. But terrible write performance, high contention, not for high cardinality or OLTP.
All right, next one sounds different. Chest, generalized search tree. What's being generalized here? And for what kind of wild data types?
GEST, it breaks the mold. It's not a specific index type itself. It's more like an extensible framework for building custom search trees. It's height-balanced, multi-way, like a B tree. But here's the key difference. The bounding regions of sibling nodes can overlap.
Overlap. Okay, how does that help?
It's crucial for indexing complex, non-traditional data types, things without a strict linear order. Geometric data, points, polygons, range types like time intervals, even full text documents. You provide extension methods, little bits of code that tell GST how to search, insert, adjust for your specific data type, and your custom operators.
So it's like a toolkit for building indexes for weird data. That flexibility must come with some performance considerations, maintenance.
Precisely. Search and GST might need to follow multiple paths because of those overlaps. Can be more complex than a B tree. And the maintenance overhead depends heavily on how efficient your custom methods are. If they're slow, the index is slow. Some implementations can also be lossy, return a few extra results that need rechecking.
Interesting. Powerful, but needs some developer care. When would an architect reach for GS?
Exactly. It's best for spatial data, time ranges, full text, custom types needing non-standard operators. PostgreSQL uses JS heavily. It powers PostGIS, for example, which uses it to implement R trees. The trade-off. Efficient reads for these complex types, but potentially higher write costs. Valuable in OLTP for specific things like location services, and great in OLF for spatial or timeline analysis. But for simple numbers or strings, B tree is way better.
Sticking with PostgreSQL's unique offerings for a moment, GIN indexes. Generalized inverted index. Inverted sounds like a flip. How do GINs handle data with multiple values in one record, like an array?
GIN, it's truly an inverted approach. Instead of mapping a record to its values, it maps each unique indexed value, a token, a lexeme, to a list of row IDs that contain that value. So a single row can appear multiple times in the index. Once for each distinct item it contains, like elements in an array or keys in a JSON-B object. The generalized part comes from operator classes that know how to extract these indexable items from complex types arrays, JSON-B text.
Okay, so if I search for, say, banana in an array column fruits, The index maps banana directly to all the rows that have banana in their fruits array.
That's exactly it. For queries, GIN gets the lists of row IDs for your search terms and does fast bitwise operations, AND or OR on those lists. Makes it incredibly fast for containment checks. Does this array contain X? Does this JSON B contain key Y? However, building this index means pulling out all those individual components, which leads to significant write amplification.
Oh, that term again. More internal work than meets the eye.
A lot more. A single row change might mean many different index entries need updating or adding. It can be heavy.
Is there anything to lessen that write hit?
PostgreSQL has an optimization called fast update. It helps. It batches new entries into a temporary pending list in memory, defers the really expensive updates to the main index structure, improves the initial write speed, but flushing that list periodically. That can still cause performance spikes. They can also take up a fair bit of memory and disk space.
Got it. Very good for specific search types, especially containment, but watch the write cost.
Exactly. Best for full-text search, array containment, JSON-B queries where you search for specific keys or values. Native in PostgreSQL, supported by ubiquitous too. Not for ranges, not for simple scalar values, not for super high write loads. Really shines in OLA for complex queries on that composite data.
Okay, we touched on spatial with geese, but for really digging into geography, multi-dimensional data, R trees are the classic choice, right? What makes them special for mapping spaces?
You're right. R trees are the specialists for multidimensional spatial data. Points, lines, polygons. They're height-balanced trees, like B trees in a way, but designed for space. They group nearby spatial objects using minimum bounding rectangles, MBRs, the smallest box that fits around an object or group of objects. And crucially, again, sibling node MBRs can overlap. That's fundamental to how they handle spatial relationships.
Overlapping MBRs again. Sounds complex for search, but maybe necessary for 2D or 3D space. How does search work?
It uses a filter and refine principle. You start at the root, check which child MBRs overlap your search area, recurse down those paths. At the leaf nodes, you refine the search, checking the actual geometry. Inserts try to find the best leaf to minimize how much its MBR has to grow. If a node overflows, it splits, just like a B tree, but the split logic is more complex.
All that MBR adjusting and splitting sounds like maintenance could be heavy. Are R trees fast for writes?
Generally, no. They are known for having costly update operations, those cascading MBR adjustments, rebalancing. It adds up. Traditional R trees also had concurrency issues, needing lots of locking. Newer variants like R-link trees improve that somewhat. They are primarily for spatial data management, GIS, CAD, location services. Queries like find within this area what overlaps this nearest neighbor.
So best suited for static or maybe read-heavy spatial data then?
Exactly. You see them in PostGIS, often via GIST, RamaDB, DuckDB. Trade-offs are okay spatial search versus costly writes. Not great for frequent updates, so less ideal for dynamic OLTP, but highly effective in OLEP for spatial analytics. Choose them when spatial is primary, especially read mostly. Avoid for high dynamic updates.
Okay, moving from spatial to textual.
Mhm.
Trie-based indexes. They specialize in strings, prefixes. If I'm building, say, a search box with auto-completion, is this the kind of thing working behind the scenes?
Often, yes. A tree, or prefix tree, is tailor-made for that. It's a tree structure where each node represents a character. Paths from the root define complete strings. Nodes automatically share common prefixes. The keys are stored implicitly by the path you take down the tree, searching for a string. Just traverse character by character, inserting. Add new nodes where the path doesn't exist yet.
Sounds incredibly efficient for anything prefix-based. Like a super organized filing system just for strings. What's the downside? Seems almost too perfect.
That's a good way to put it. They are extremely fast for prefix matching, auto-completion, great for dictionaries, spell checkers, even network routing tables doing longest prefix match. The primary drawback, though, is potentially high space requirements. A naive trie node might need pointers for every character in the alphabet, even if only a few are used. Can get sparse and big.
The memory usage.
Exactly. So lots of compaction techniques exist. Tailhead compression, advanced structures like Judy arrays, RT, ATT tries, all trying to mitigate that space issue. Concurrency can also be complex, but modern versions like concurrent hash tries or C trees offer lock-free scalability using atomic operations. Very clever stuff.
So high performance for string tasks, but you really need to watch the memory footprint and maybe use advanced versions.
Yes, you find them in systems like ExtremeDB. Some distributed DBs like Cassandra might use trie-like structures internally for partitioning or key management.
Yeah.
Trade-offs. Very fast prefixes X string lookups. Writes vary, can depend on key length or entry count. Memory overhead is the big watch out. Choose them when strings dominate and you need that prefix matching or auto-completion.
Okay, we keep coming back to text. And inverted indexes, often called the backbone of search engines. What makes them so good at finding relevant stuff in massive amounts of text?
Inverted indexes really do flip the perspective. They store a mapping from content terms, words to their locations in documents. It's a reverse mapping, term to document. It usually has two main parts: a vocabulary, all the unique terms, and posting lists. For each term, a list of document IDs where it appears, often with frequency or position info.
Right, so when I type into Google, it's looking up my words in this massive inverted list to find the documents.
That's the core idea. When building the index, documents get parsed, tokenized lowercase, common words removed, stems found, then the vocabulary and posting lists are built. When you query, your terms are processed the same way. The system looks up their posting lists and combines them using set logic, AND, or R. Then, ranking algorithms like TF-IDF or BM25 kick in to sort the results by relevance.
Sounds like a lot of work when a document is added or changed. Tokenizing, updating lists. How do they handle frequent updates, like on a busy website?
They do have high maintenance costs for updates, deletes, inserts. It's significant. Real-world search engines like Elasticsearch or Solr, which use Lucene underneath, handle this cleverly. They achieve near real-time indexing. They do this by creating new, small, immutable index segments for recent changes. Then, in the background, they merge these segments together. Deletions are often marked with tombstones initially and fully removed during merges. It trades background processing work for immediate queryability.
Ah, the segment merging approach. Clever.
It works well. The main trade-off is very fast reads for full text search, but significant write amplification and potentially large storage overhead, though compression helps a lot. They're the cornerstone for search engines, document retrieval, log analysis. PostgreSQL's GIN is actually an implementation of this inverted index concept.
Fascinating. Okay, from huge search engines to something maybe lighter, zone maps or min-max indexes. These sound like they're more about data skipping. How do these help analytical databases?
Zone maps, or min-max indexes, yes, they're lightweight, very different. They store summary statistics, just the minimum and maximum values for contiguous regions of data. These regions are often physical blocks or groups of blocks called zones. They are much more compact than a typical row-level index like a B tree. Their main job is data skipping or pruning during range queries.
So like a quick check. Is it even possible for the data I want to be in this huge chunk?
Exactly. The database checks the zone map first. If your query's filter range say where timestamp between X and Y doesn't overlap with a zone's min-max timestamp range, that entire zone is just skipped, not read from disk at all. Drastic I/O reduction.
That sounds perfect for large analytical tables, especially things like time series data.
Precisely. They are best in columnar systems, OLTP, data warehousing. Especially effective when data is clustered or nearly ordered, like those datetime columns. They're often generated automatically by the database system, so maintenance overhead is very low. You'll find them in DuckDB, Oracle, Exadata storage indexes, cloud data warehouses like Redshift, Snowflake, BigQuery use similar concepts.
Yeah, huge read gains for analytics. Almost no write impact. What's the catch? Is there one?
Minimal impact on writes, highly space efficient. The main catch, if you can call it that, is they might be slightly stale within a transaction until it commits. That's usually fine for OLTP analytics, but wouldn't work for OLTP needing real-time consistency for single lookups. And they're ineffective if the data is totally random. No skipping possible then. So not a B-tree replacement for transactions, but a fantastic optimization for analytics.
Right. Now let's talk about systems drowning in new data. LSM trees, log-structured merge trees. These are all about write-heavy workloads, aren't they? How do they flip the script?
LSM trees, yes, they are fundamentally optimized for write-intensive workloads. They are revolutionary in that sense. Their core trick is transforming random writes into sequential writes, minimizing that slow disk seek time. How? They buffer all new writes into an in-memory structure, usually called a memtable. It's sorted. This is also written to a write-ahead log, the vol-ual, for durability. When the memtable fills up, it's flushed to disk as an immutable, sorted file, an SS table, or sorted string table.
Okay, so writes go to memory first, then flushed sequentially. But you end up with lots of these scamble files. How does that work for reads?
You do end up with multiple SS tables organized in levels, L0, L1, etc. And that's where the other critical part comes in, compaction. Compaction is a continuous background process. It merges and reorganizes these SS stables across the levels. Its job is to consolidate data, remove deleted or updated by reducing the number of files to check, and optimize storage space. There are different compaction strategies like leveling or tiering with different trade-offs.
So reads have to check the mem table and potentially multiple SS tables across these levels.
Correct. Point lookups check the mem table first, then search downwards through the SS table levels. They often use Bloom filters, probabilistic data structures, to very quickly tell if a key cannot be in a specific SS table, avoiding unnecessary reads. Range lookups need to collect relevant entries from the mem table and all relevant SS tables and then merge them on the fly.
Sounds powerful for writes, but compaction and multi-file reads, what are the overheads?
They definitely have inherent overheads, often talked about as amplification. Write amplification. Your single logical write might cause data to be rewritten multiple times during compactions. Read amplification. A single logical read might need to check multiple places, mem table, several S tables. Bloom filters help, but it's still there. Space amplification. Alt versions or deletion markers, tombstones, take up space until compaction cleans them up. And compaction itself can cause I/O spikes or jitter, requires careful tuning.
But the payoff is that write throughput.
Exactly. They excel at very high write throughput. Think logging, IoT data streams, real-time analytics feeds, key value stores, NoSQL databases. Highly suited for SSDs because they turn random writes into sequential ones. You find them everywhere now. LevelDB, RocksDB, HBase, Cassandra, TiDB, MongoDB's WireTiger uses them, Spanner. They naturally support MVCC for concurrency too. Choose them when writes dominate and you can tolerate slightly higher or more variable read latency.
Okay, fascinating. Now let's get really cutting edge. AI territory, vector indexes or ANN indexes, approximate nearest neighbor.
Yeah.
How are these finding similar things in ways traditional indexes just can't?
Vector or ANN indexes, yeah, they're a different beast entirely. Designed for high-dimensional data points, vectors, often the output of machine learning embeddings. Their goal is an exact match, but finding close or similar vectors based on some distance metric, like cosine similarity or Euclidean distance. The key is approximate in AN. They trade a little bit of accuracy. You might not get the absolute single nearest neighbor for dramatically faster search speed, which is crucial when you're dealing with billions of vectors in AI.
Right, approximate but fast. What are some common types? I've heard names thrown around.
Several popular approaches exist. HNSW, Hierarchical Navigable Small World, builds this clever, multi-layered graph structure. You can jump across layers for speed, then navigate locally for precision. Annoy Approximate Nearest Neighbors, constructs multiple random projection trees and combines the results. And Facebook AI Similarity Search isn't one algorithm, but a whole library offering various strategies, including IVF, inverted file index for vectors, product quantization, PQ for compression, and HNSW implementations. Often supports GPU acceleration, too.
Okay, different strategies. How do they handle updates? If my vectors change or I add new ones, that seems tricky for these complex structures.
It varies significantly, and it's a really important distinction. Annoy indexes are generally immutable. Once built, you often have to rebuild the whole thing to incorporate changes. Not great for dynamic data. HNSW, on the other hand, actually excels at dynamic updates and inserts. Adding a new vector to the graph is relatively efficient. Deletions are more complex, though, needing graph link repairs. Face supports dynamic operations, too, but depending on the chosen index type within Face, it can be computationally expensive.
Interesting. So HNSW is better if your vectors are constantly changing.
Generally, yes. HNSW is often preferred for dynamic use cases. These indexes are best for similarity search, finding similar images, audio clips, text embeddings. Recommendation systems use them heavily. E-commerce search, multimedia retrieval, NLP tasks like finding semantically similar documents. And they're absolute crucial for error retrieval augmented generation powering many modern LLM applications. You find these algorithms in dedicated libraries like FAIS, Annoy, HNSW-lib, used in systems like Google Stan, and in purpose-built vector databases like Milvus, Pinecone, Chroma. Traditional databases are adding vector search too.
Trade-offs seem to be speed versus accuracy and how well they handle updates, plus memory usage.
Exactly. Very fast approximate reads, tunable accuracy versus speed. Write performance varies massively. Memory disk usage also varies. HNSW can be memory hungry. Annoy can be more efficient or disk-backed. Concurrency is generally handled, but deletions can be tricky. Choose based on your need for dynamic updates, scale, memory constraints, and if you need GPU support, AAIS.
Wow. Okay, finally, let's touch on the real frontier. Learned indexes. This sounds like sci-fi, an index that learns. What's the magic trick? And are they about to replace everything else?
Learn indexes, yeah, it's a fascinating, very active research area. Not quite sci-fi, but definitely bleeding edge. The core idea is to use machine learning models to predict the position or offset of a key within a sorted dataset. Essentially, the model learns the cumulative distribution function, CDF, of your data. It learns how your keys are spread out. So when you search for a key, instead of traversing a B tree, the model makes a prediction. This key is likely around here. Then you do a very small localized search, like binary search, in that predicted area to find the exact key or confirm it's not there.
So it replaces the tree traversal with an ML prediction plus a tiny local search.
That's the goal, aiming for lower query latency and potentially smaller index size compared to traditional structures like B trees, especially for large data sets. They often use a hierarchy of models. A root model points to smaller, specialized models for different data ranges.
It's an incredible concept. But what happens when the data changes? Doesn't that mess up the model's learned distribution?
That is the biggest challenge. Insertions and deletions absolutely alter the data distribution, potentially making the model's predictions inaccurate over time. There are strategies to handle this, reserving gaps in the data structure, using temporary delta buffers for new inserts, designing bucket-based learned indexes. But the most significant maintenance overhead is model retraining. As the data drifts, the model needs to be updated or completely retrained, which is computationally expensive and time-consuming, especially if the data is on disk.
The retraining costs. So they're not a universal replacement yet. Where are they best suited today or showing promise?
They show the most significant promise in read-heavy scenarios, especially where the data has a simple, smooth, predictable distribution that ML models can learn easily. They've shown impressive performance gains, particularly in in-memory databases, where the cost of running the model prediction, inference, is very low compared to disk access. They can offer lower lookup latency and sometimes smaller index sizes in these specific cases. However, they generally perform worse for write-heavy workloads due to that retraining cost. They struggle with complex, unpredictable data distributions, and they don't inherently offer much advantage for range queries or complex string keys compared to B trees.
So niche applications for now, mostly read-heavy, predictable data, often in memory.
Pretty much. It's an active research area. You see ML being used for index automation in systems like Oracle Autonomous Database or Azure SQL, deciding which traditional indexes to build, rather than replacing them entirely with learned structures yet. There are many research prototypes, RMI, radix spline, PGM index, ALX feeding tree, pushing the boundaries. But for general purpose use, traditional indexes still dominate for good reason.
What an incredible journey through the hidden world of database indexes. Wow. From the tried and true B trees, which we all kind of take for granted,
Right.
all the way to these cutting-edge learned and vector indexes, it's crystal clear there is no single best index, no silver bullet.
Indeed, not at all. Each index type is really a finely tuned instrument, designed with very specific internal mechanics, specific algorithms, and crucially, specific trade-offs in performance, storage, and maintenance. The real, well, joy of architecture, you could say, lies in understanding these nuances. Making those informed decisions based on your specific data, your workload patterns, and the context of your system, OLTP, OAllow, distributed, embedded, it all matters.
It really makes you think, doesn't it? What kind of data problem are you, our listener, trying to solve next? How might understanding these internals, the B-tree rebalancing, the LSM compaction, the ANN approximation, change how you approach your next big architectural challenge? We really hope this deep dive into the mechanics and trade-offs of database indexes has given you some powerful new insights, maybe sparked some ideas. Thank you so much for joining us on this exploration of the joy of architecture. If you enjoyed this and want more deep dives into the topics that really matter in system design, be sure to subscribe wherever you get your podcasts. We'll be back soon with more fascinating insights.